And I want to start the process in earnest for deducing something about a function f if we know that its U3 norm is reasonably large. So by reasonably large, what I mean is this. I'll assume that the function f takes values in -1, 1. Then we know that the U3 norm is trivially bounded above by 1 if it's at least some absolute constant c positive. Then we will regard it as large. So c we think of as a fixed positive constant, and the size of the group that we're talking about tends to infinity. So before I get going with that, I want to start by proving an inequality that I'm going to use, which is called the box norm inequality. And before that, I need to define the box norm. So it's given by, so supposing I've got x and y finite sets, and f maps x cross y to complex numbers. Then we define the box norm f box by the formula box norm to the 4 equals the average over all x, x dashed, y and y dashed of fxy, fxy dashed, fx dashed y, fx dashed y dashed, and we put complex conjugates over the ones where we've got an odd number of dashes. The proof that this is a norm is rather similar to the proof that we used for the U2 norm and U3 norms. So you look at 4 different functions, you prove a kind of box Cauchy-Schwarz inequality, and from that you deduce in a straightforward way the box norm inequality. But I think I'll leave that as an exercise on the next sheet. But actually something that follows from the box Cauchy-Schwarz inequality, but as a simpler special case of that, is what I refer to as the box norm inequality. And it says the following. So let x, y, and f be as above. Then, and also, let u be a function from x to the complex numbers and v be a function from y to the complex numbers. Then the average over all x, y, fxy, ux, vy, which if you think about it, if you think of f as a matrix indexed by x and y, then this is the inner product of u with the matrix applied to v. So one can think of this as or we can think of it as a bilinear form, if you like, as well. But anyway, that is less than or equal to the box norm of f times the L2 norm of u times the L2 norm of v. And the proof is, again, one way we just sort of Cauchy-Schwarz our way to our destination. So for that purpose, I'll begin with squaring the modulus, because, as always, it's not very easy to deal with modulus on its own, unless you're just going to apply the triangle inequality or something, but we can't afford just to do that. And now I'll apply Cauchy-Schwarz, or the sort of elementary special case of it that the average, or the square of an average, is at most the average of the square. So that's less than or equal to the average over x, and I'll take everything out. Actually, I'm going to think of this as average. I'm sorry, just by Cauchy-Schwarz. Average over x of ux times the average over y of fxy vy. So if I think of my two functions as ux and average over y fxy vy, then apply Cauchy-Schwarz, I get one contribution looks like that, and the other contribution looks like this. And that equals So the first bit is nice because I've got the u2 I wanted. Notice that I squared the left-hand side, so that's good. And then this part here, I'm going to do a bit of multiplying out and rearranging and so on. So that'll be e of y and y dashed, e of x. Actually, let's take out the v terms as well. So vy dashed bar, and then I just, so general rule is I move my expectation things past everything that doesn't depend on the dummy variable in question. So then I'm left with fxy dashed bar, and this thing happens to be a non-negative real, but I could, if I wanted to, put mod signs around everything, and it would still be less than or equal to. So by Cauchy-Schwarz again, that's less than or equal to the u2 norm of u. Now I'll apply Cauchy-Schwarz to with this y dashed, so it'll be at most ey y dashed vy dashed squared. This time, because I haven't squared everything, I do have to put the half in. And here I get average over y dashed average over x. So this is the rest of the function. Now if we look at this, what does it equal? Well, that mod squared of the product is the same as the product of the mod squareds, and we're taking the average over two completely independent variables, so that's just going to give us inside this bracket the square of the average of the squares, in other words the fourth power of the L2 norm, and then I got this to the half. So that'll be equal to the thing that I had here before, and the square root of the fourth power of the L2 norm of v, in other words the square of the L2 norm of v. And if you think about what happens inside the brackets here, when I expand this out, I'll get an x and an x dashed, and I'll get two terms like this, except with x dashed in them, and complex conjugated, and that will give me precisely this expression here. So that is the box norm of f to the 4, but then to that half power gives me a squared there. And slightly confusingly, I use a box symbol to end the proof. So that's that lemma done. Now let's make a little observation about, so now I'm going to let, I think I'm going to specialize to the FP case. Actually in the notes I did this for, it just proved something slightly more abstract for an arbitrary finite abelian group, but I'm going to, since we're doing fp to the n, I'm going to have f is a function from fp to the n to the complex numbers. And we're going to assume that its L infinity norm is at most 1, and that its u3 norm to the power 8 is at least c. And the question is, what can we say about f? Well, let's start with the observation that the u3 norm to the 8 is the average over all a of the u2 norm of the difference function, so that should be u2 there, to the power 4. Now, if you don't see that immediately, I recommend you write it out. I'll just say what happens. So each partial a of f evaluated at some w or something will give you f of w times f of w minus a bar. So when you take the u2 norm raised to the power of 4, you're going to have that for a particular a, so a function that goes, well, if evaluated as x, gives you f of x minus a bar. Then you can take that whole thing and subtract b from everything and put a bar on it, which will, and then a c, and then a b minus c, or b plus c you subtract. And you find out what you've ended up writing at when you've written out this in full. Is precisely the formula for this written out in full. But that equals, so the sum over all r, now this r belongs to the dual group of fp to the n, so that's basically the same as fp to the n, except we use the counting measure rather than the probability measure, of delta a f all hat of r raised to the power 4. That's because, if you recall, that the u2 norm raised to the power 4 is the L4 norm of the Fourier transform raised to the power 4. And so all that was at least c. So also we have that this is less than or equal to 1 for all a and r, since f is bounded between -1 and 1. So if you just look at the formula for this, you'll see that it's quite clearly less than or equal to 1. And so this means that we can do something a little bit, normally would be a little bit naughty, and just say that's at most the average over a. Actually, so that's not quite what I want to say just yet. Oh yes, so this sum over all r, so this is less than or equal to the average over a. So I wanted to say something slightly different here. So let me just say what I want to say, and then I'll justify it afterwards. So that's less than or equal to the average over a times the maximum over r of that squared. And that's because the sum over all r of delta a f r squared is the L2 norm of delta a f squared, which is less than or equal to 1 because f has an infinity norm at most 1. So by averaging, or by one of the inequalities that we used earlier, a sort of ugly inequality, for at least c g, so g is the same as fp to the n, so this size is p to the n. So cgn over 2 values of a, we have that the maximum over all r of delta a f r squared is at least c over 2. If we didn't have that, it's quite easy to check that this thing here could not be at least as big as c. Right, so now let B equal the set of A such that this holds. I better write it again. And let phi from B to fp to the n, I'll put a hat on just to emphasize that it's really, I'm thinking of it as the dual group, be such that so I'm going to choose some function such that delta A f hat of phi A squared is greater than or equal to c over 2 for all A belonging to B. So why can I do that? Some people find this a little bit confusing, but it's actually one of those things that's essentially trivial. So if I've got an A and B, then I know that this maximum is at least c over 2. So there must be some r such that this takes the value at least c over 2, and I shall just choose one such r. I don't care how I do it. I'll just, for that r, I'll choose some r that works for the given A, and I'll call it phi of A. So I may have lots of different choices for phi of A. I don't care. I'll just choose one arbitrarily. And so now we have that just the key inequality we have is that, well, it is this inequality here. And then the other inequality that matters is that the size of B is at least C times the size of G divided by 2. So now I'm going to define, actually no, let's prove something. So the average over A of B of A, so that I mean as just 1 if A is in B and naught otherwise, of partial A f hat of phi of A squared is greater than or equal to, right, the probability that A belongs to B is c over 2, and if A belongs to B, then this quantity here is at least cg over 2, but I'm averaging, so I get c over 2 squared. If you like, I suppose we could set phi of A to be arbitrary if A does not belong to B, and then it doesn't really matter because I'll then be multiplying this thing by 0 anyway. So now let's do some expanding. So c squared over 4 is less than or equal to EA BA, and now let's expand this thing out. So in fact I'll do it in 2 steps. So it's I'm going to write a formula down for I need to put an expectation over x in here, and then I have f of x minus a, so that's partial a of f evaluated at x, and then I have omega to the minus phi of a dot x. So phi of a is an element of fp to the n hat, and then a square there, which equals average over a b of a average over x and y fx minus a fy bar fy minus a omega to the minus phi a dot. Then I have a contribution from an x and then a contribution from a y, but conjugated, so I get x minus y there. And now I'm going to do a little sort of trick in a sense. I'm going to change variables. So instead of x, y, and x minus a, y minus a, I'm going to make y into x minus b and x minus a into y. In fact, I think I don't even want to change the names of the variables. So y is going to be called x minus a. It's not the same as this a. You can think of it as x minus b, but then I change the name from b back to a. And x minus a is going to be called y in my change of variables. So that's the average over a. And I've got to be a little bit careful. So what is a now? If I'm calling this y, then this old a is x minus y. So I'll put, let's put the x, y over here to be completely safe. B of x minus y, then f of x, f of y bar, f of x minus a bar, f of y minus a, omega to the minus phi of x minus y. So a recall has changed to x minus y, and x minus y has changed into an a. If you found that confusing, I recommend choosing different letter names, calling this one Z and calling the new A and a B or something like that. But I somehow want to emphasize that we've just swapped A and x minus y around, and that was an entirely legitimate thing to do, because it's all we've done is a change of variables. Now, why did I want to do that? It's because for each A, I've got a function b x minus y phi x omega to the minus phi x minus y, and then I've got something that depends only on x for constant a, and something that depends only on y. So I can apply the box norm inequality. It's the average over a. So I'm applying the box norm inequality to the two variable function bx minus y omega to this lot, and then the two one variable functions fx minus a bar and fy minus a bar. And I'm going to use the fact that f has L infinity norm at most 1 to say that the L2 norms that come out of the box norm inequality are at most 1. So I can just ignore all these f's here and just take the box norm of the function, which I'll just call this is a slightly unpleasant notation. So this inside here is not a function, or the way I've written it, it doesn't look like a function. It looks as though it's evaluated at some points, x and y and so on. What I mean by this is the function that takes x and y to this expression here. So if you want to be a bit more correct about it, you might sort of, I don't know, could use lambda calculus or something to make this into a function. And now I'm going to say that that is, or yeah, I could say, perhaps I'll be a bit more correct about it. Here's how to be more correct about it. So the average over A of box norm of GA, where GA of XY equals this. So there we go. Perhaps that's a bit nicer. But the average of GA box to the fourth power, to the fourth power, and in fact I'm going to say so we knew that c squared over 2 was at most this thing here, so c squared over 4, so c squared over 4 to the 4 is less than or equal to this thing here, which by Cauchy-Schwarz applied twice is at most the average of the 4th power of the box norms. And so I did that because I know how to expand the 4th power of box norm, but I didn't know how to expand just the box norm itself. And so that equals the average over A. And now let's write a few things down. So average over x plus y equals, am I going to get into trouble if I do this? Sorry, x dashed y dashed, and here we go. So b x minus y, b x minus y dashed, b x dashed minus y, b x dashed minus y dashed. I don't need to put complex conjugates because b is a characteristic function, but here I will need to omega to the minus phi, or minus big brackets, phi x minus y minus phi x minus y dashed minus phi x dashed minus y plus phi x dashed minus y dashed. So these signs came from whether or not I needed to take a complex conjugate, all dotted with A. And now a very nice thing happens, which is that when I take the average over A, this entire thing is going to be 1 if the thing in brackets is 0 and 0 otherwise. So we end up with the average over all x dashed y dashed such that actually I'm going to do something else first. So I'm going to observe that if we look at these 4 variables and think about what happens to these 4 expressions, so that one plus that one equals that one plus that one, and those are the same, so that one plus that one equals that one. And so in fact those 4 expressions inside the brackets range uniformly over all additive quadruples. So this is in fact exactly the same as average over all A, average over x I'll write it like this, just x minus y minus z plus w equals 0 of bx, by, just to make the order the same as we have up here, bz, bw, omega to the minus phi x minus phi y minus phi z plus phi w dot A. And now when I take the average over A, if this is 0 I'll get 1, if it's not 0 I'll get 0. So this is equal to the average over all x, y, z and w such that x minus y minus z plus w equals 0 and phi x minus phi y minus phi z plus phi w equals 0. So then I just write this bx, by, bz, bw. So if we say that x, y, z, w is phi-additive, if x minus y equals z minus w and phi x minus phi y equals phi z minus phi w, then B, which is a subset of G, contains at least c squared over 4 to the 4, so c to the 8 over 2 to the 8 G cubed additive quadruples. phi-additive quadruples. Another way of saying that is that the graph of the function phi contains at least this number of additive quadruples. And now we see the reason I wanted to talk about the Balog-Szemerédi theorem earlier on in the course, because we are going, not in this video but in the next one, to exploit very much the fact that B contains many phi-additive quadruples. That's going to turn out, if we apply the Balog-Szemerédi theorem and then Freiman's theorem for finite fields, it's going to imply that phi agrees quite a lot with a linear map, and that is going to be very significant. But that is for another video, and I will stop this one at this point.